Today I am going to discuss the stoichiometry of bioprocess. Now, if you look at the stoichiometry that of the bioprocess, that gives the three different informations. First, it gives the information to study the quantitative relationship between the amount of the reactant used and the amount of product formed by a chemical reaction or mutual relationship and internal limitations within the biochemical system. That means what we want to say, that how much of substrate reacts to give how much of products, that information we can generate. Then this also gives us the information about the validity of the experimental results. This is this I shall show you how it can be done. And another is the heat evolve in the aerobic fermentation process. As you know, most of the biochemical reaction, they are exothermic in nature. So during the reaction some heat evolve take place. So most of the biochemical reaction, usually most of the microorganisms, they grow close to the ambient temperature and pressure, atmospheric pressure. So if the temperature shooted up, particularly during summer, we are in the tropical country, and in summer our temperature as high as 40-45 degrees centigrade, and whereas the temperature of the fermenter is 30-35 degrees centigrade. Naturally the temperature shooted up, so we required some kind of cooling arrangement. So if you want to calculate how much heat is evolved during this process, that we can easily find it out. And stoichiometry is basically based on law of conservation of mass. That if you look at this equation, the things will be very clear, that mass in through the system, mass in through the system boundary, what is coming in, and mass out through the system boundary. So something is coming in and mass is coming in and mass is going out, and plus mass generated within the system minus the mass consumed within the system, that is equal to mass accumulated within the system. This is a kind of law of mass balance equation that we have in this particular system. Now the elemental balances, we have a material balance on biological reactions can easily be written when the composition of the substrate, products and cellular materials are known. So here I want to tell you that whenever we want to do some kind of stoichiometry of bioprocess, we should have some kind of information that what exactly going on in the biological process. Then and only then we can do the stoichiometry. As for example, suppose we want to use some kind of carbon source. Suppose we want to use glucose for the cell mass production. So glucose is converted to cell mass. It is not producing other than the cell mass. But the glucose, when it produces ethanol, we are targeting only ethanol, not the cell mass. So naturally that our stoichiometric equation will be little bit different. So this is very important. Usually the electron proton balance is required in addition to elemental balances to determine the stoichiometric coefficient of the bioreactor. So this is, I shall show you how it can be done. Accurate determination of the composition of cellular material is a major problem. The typical cellular composition represented by CH 1.8, O 0.5, N 0.5. So biomass composition, we approximated like this. We find it is variation is plus minus 5%. So it is quite acceptable. And 1 mole of biological material is defined as the amount containing 1 gram atom carbon, such as C, H alpha, O beta and N delta. Now here the elemental prevalence I have shown in a particular equation, the macroscopic mass balance of the microbial system concerning the biomass production and another product can be written in its original form. This is the substrate. I can write in the elemental form. This is we call empirical formula, but this is on the basis of per carbon atom substrate, per carbon atom biomass, per carbon atom product. So this is, as you know, that for the formation of the cell mass we require nitrogen source, and also most of the biochemical process they are aerobic in nature, we required oxygen. So it gives the biomass, then it gives the product, then due to respiration and other reaction it produces carbon dioxide and water. The composition of substrate, biomass and the product in the equation are expressed by the elemental chemical analysis. Now we come across one new term that is called degree of reduction. Degree of reduction means number of free electron in that quantity material containing 1 gram atom carbon. That I can tell you, as for example biomass, if you look at the biomass, now in the biomass this is the formula of biomass. Now this is the carbon, hydrogen, oxygen and nitrogen. Now what do you consider that in case of free electron, if you look at in case of carbon we have 4 free electrons, in case of hydrogen we have 1 free electron, and in case of oxygen it always take 2 electrons because it has 6 electron in the outermost orbit, so it can take 2 electrons, and minus the 3 electron except by the nitrogen. So this is how we can write the free electron balance. Now if you consider this is biomass, the issue will be what? 4 plus P minus 2N minus 3Q. Here what exactly you can find, this is like this. And similarly product also we can write like this. If you look at the product, that is it is 4 plus R minus 2S minus 3T. In case of substrate, what will be there? 4 plus M minus 2L. So this is how we can write that how much free electron present per gram atom of biomass, per gram atom of product and per gram atom of substrate. But there is no free electron of the metabolic end products such as water, carbon dioxide, ammonia, while oxygen in the form of O2 accept 4 electrons. So this is the basis on which we can do the stoichiometric analysis. So this is the point that we shall have to keep it in mind when we do the stoichiometric analysis of the bioprocess. Now I have given some typical example in this table. You can see the different biomass, and I have given the empirical formula of the biomass, and you see that if you do the free electron analysis of this biomass, you will get this figure. So degree of reduction of the different biomass is different, though they are very close to each other, but they are different from each other. Standard deviation is 3%. Now we have taken the example of one particular biomass, what you call Escherichia coli. The E. coli is largely used, and its formula we are estimated as CH 1.77, O 0.49 and N 0.24. Now P will be what? P is one carbon, the 1.7, N is 0.49 and Q is, so we can if you write the degree of reductance, so it is what will be 4 plus 1.77, 1.77 minus 2 into 0.449 minus 3 into 0.24. So it is coming 0.47. So we can easily do these calculations. Now I have given other examples of different substrates, as for example alkanes like methane, hexane, hexadecane, then alcohol, methanol, ethanol, that we have ethyl glycol, glycerol. So different you can easily do by yourself and check whether you are coming you are getting this figure or not. Now the oxygen requirement is directly related to the electron available for the transfer to oxygen, because this is very important. From this we can easily I shall show you how you can find out the heat evolved in the fermentation process. Now if you want to do the electron balance of this equation, that we have the previous equation that we have here, that we have substrate, we have oxygen, we have biomass, we have product, because I already told you ammonia the free electron of ammonia will be 0, free electron of carbon dioxide is 0, and free electron of water is 0. So if you do this free carbon balance, then how you do that? Number of available carbon in the substrate plus number of available carbon in oxygen equal to number of available carbon in biomass and number of available carbon in product. So if you do this, you will get this equation. The gamma S is the degree of reductance of the substrate, and B is the moles of O2. One O2 give 4 electrons, and then gamma the YC is the, if you look at YC is the YC 1 gram atom biomass, YP 1 gram atom product, like this that we have. So if you, that is why what we have written here, YC into gamma P is the degree of reductance of biomass, and YP and gamma P this is multiplied by this. Now if you divide by 4, we will give the B, and B is the oxygen that is demand in the process. So we can easily calculate how much oxygen required in the system if you have these informations. Now if you in this equation, if you we can divide by gamma S, and you will come across this kind of equation, and if when you come across this kind of the equation, we have 3 different fractions. These fractions indicate it is the fractions of available electron transferred from the substrate to oxygen, and fraction available electron transferred from substrate to biomass. This is biomass, while gamma B is the biomass, and this is the gamma P. So this is the fractions available electron transferred from the substrate to product. So I hope it is clear that three different fractions indicate the different things, because different information gives us the 3 different informations. Now second information that we have, what you call eta equal to YC gamma B by gamma S, this is called energetic growth yield. This is called energetic growth yield, and if epsilon P, it is called as energetic product yield. So the two information is very much required. That is because why we require this, because we know I shall show you the thermodynamic efficiency of any biological process depends on these 2 factors, because this is nothing but eta plus epsilon P. Now another way we can have the analysis, that is another way characterizing the compound participating in the microbial process, is to use the weight fraction of carbon in the organic matter defined by the following relationship. As for example, suppose we have biomass, we have the formula of biomass. So we have 1 gram atom biomass, that is equal to 12 gram, because the atomic weight of biomass is 12. Then if you look at the formula is 12, what is the molecular weight of the biomass, 1 gram atom of biomass, that if you multiply this, oxygen will be 16, nitrogen will be 14, and hydrogen will be 1. If you put this value, then you will get the sigma B, then sigma P also you can go, and sigma S also. So this fraction basically deals with that with respect to carbon, the per gram of biomass, how much carbon is there. That is, this fraction deals with like this. This information we can get from this. Then in case of biomass, production of the above formula are not adequate for solution the unknown coefficient, another experimental quantity is required, that is the biomass yield. That is, biomass yield we can easily calculate when you carry out any kind of biochemical processes. If you look at, suppose you carry out any fermentation process, you grow the cell mass inside the reactor, and after some time you take out the cell mass and determine how much cell mass is produced. because that is nothing but equal to the final cell mass concentration minus the initial cell mass concentration divided by how much substrate is consumed, that is my S0 minus S. S0 is the initial substrate concentration and S is the substrate concentration of the sample that you have taken out from the reactor. So, you can easily calculate the yield coefficient. This is gram of cell produced per gram of substrate consumed. So, then we have y, this y x by s can be influenced by the composition, nature of carbon, nitrogen source, pH and temperature. As you know, biological system, I told you in the early classes, they are very sensitive to the environment. As you change the environmental parameters, your composition, your cell mass yield, everything will be tell. It depends. It is very, because I have given the example that in our human system also, suppose if we increase the temperature of this room to 40 degrees centigrade, we will be reluctant to work, because 40 degrees centigrade is very high, 45 degrees. Similar to the microorganism, they are very sensitive to the environment. So, if you keep the condition as the good, then and only then you will get the your yield will be more. The biomass is greater in the aerobic than the anaerobic culture. This is very important, because if you look at the aerobic fermentation process, we get more cell mass production as compared to anaerobic fermentation. So, in other way we can tell the nutritional requirement for the anaerobic fermentation process is much less as compared to the aerobic fermentation process. And then we can evaluate this y x by s is the gram of cell produced per gram of substrate. Now, if you multiply if you divide by the molecular weight of this substrate and molecular weight of the cell mass, then you can easily convert it to C, and this is C is nothing but YC. You can see that we have already, if you look at our equation, that here you have YC. What is the value of YC? You can what is this? This is YC equal to that gram atom of biomass produced per gram atom of substrate. That is the ratio that you have, that you can calculate here. Here you can calculate, if you divide by the molecular weight, you can get the gram moles per gram atom substrate. You can easily find it out. Now, this can be again expressed at y x by s can be expressed as eta. Eta is the energetic yield coefficient, sigma s, gamma s, sigma b s, gamma b. So, this I have already explained, the sigma s, gamma s, the atomic weight of carbon, molecular weight of substrate, and y x by s equal nothing but x a minus x 0, s 0 minus s. So you can, if you suppose if you know the why it is required, because suppose you carry out some kind of, I told you the stoichiometry of the process gives you the information on the validity of your experimental results. Now, suppose you experimentally you find out the cell mass yield, that you can easily find it out, because you know the final cell mass concentration minus the initial cell mass concentration divided by initial substrate concentration minus final substrate concentration. The ratio give you the yield coefficient. Now, this for when you write the stoichiometric equation from the empirical formula of the substrate and the biomass, you can easily find out the value of sigma s and gamma s, sigma b and gamma b. You can easily estimate. So, if you know this, and though you can find out the eta value. Now, I told you thermodynamic yield coefficient, that is nothing but eta plus epsilon p. So, from that we can find out that now in case of aerobic process, I will show you, this is varies from 0.5 to 0.6, and in case of anaerobic process it is 0.7. So, if this value comes within this range, that means your experimental results is right. And if this results varies from that, there is something wrong with the experimental results. I said we will solve some problems subsequently. So, yeah, I think the problem, these things will be very clear to you. Now here regarding the product synthesis introduces one extra unknown stoichiometric coefficient to the equation, an additional relationship between the substrate and product is required. The term is called product yields. So, what is this? Y P by S is what? Gram of product from per gram of substrate produced. So, this ratio is gram by gram, that is the dimensionless. Now, here also you can easily find out the value of this in the terms of gram atom gram mole of product from per gram mole of substrate consumed. So, in this equation, that in your stoichiometric equation you have seen before, that that here that the Yp value that you can easily calculate it from this equation, that also you can easily find it out. Now, Yp by S, again it can be written as epsilon P energetic product yield, and this is sigma S by sigma gamma S and sigma B by gamma P. So, this ratio you can easily find out this, and Yp by S equal to P is the final product concentration minus in P0 is the initial product concentration, S0 is the initial substrate concentration minus S. So, you can find out that gram of product form per gram of substrate consumed. So, similarly we can calculate y x by x by O, x by y x by S is a gram of cell produced per gram of oxygen consumed, 3 eta 2 sigma b gamma p 1 minus eta minus epsilon p. So, this also this equation we can use, we can directly calculate how much cell mass is produced per gram of oxygen consumed. Now, I was talking about the thermodynamic coefficient of the bioprocess is given by eta and epsilon, and range of thermodynamic coefficient for the aerobic fermentation process is 0.5 to 0.6 and approximately 0.7 in case of anaerobic. So, this you have to remember that when you want to find out the stoichiometry of the biological, suppose you do not have the information of eta, and some I can give little bit of example. Suppose anaerobic digestion process. Anaerobic digestion process, what we do basically, we produce methane and carbon dioxide from the organic waste. Now, it is the anaerobic fermentation process through which we get the methane and carbon dioxide. Now, here since it is anaerobic fermentation process, I told you the cell mass growth in aerobic process is usually 10 times as compared to that of anaerobic fermentation process. So, we can we can ignore the amount of cell mass that produce in the anaerobic fermentation process. So, in that case the thermodynamic coefficient we can assume to be 0.7, because that eta value in case of this anaerobic fermentation process, this thermodynamic coefficient it should be equal to 0.7. Now, if there is a variation of the value from 0.7, then we shall have to check that experimental results, there is a possibility of the error. So, if you correct this error, and then you will find that value will be coming close to 0.7. So, it is a good method, it is a very nice way to detect the error of your experimental results. Now, I told you another thing that heat evolved by the anaerobic fermentation process also can be determined with the help of stoichiometry of the equation, because particularly aerobic process we required oxygen, and because oxygen is required for both for the aerobic and anaerobic process, as you know that in the aerobic process the organism required the molecular oxygen, aerobic process they required molecular oxygen, but anaerobic process they take the oxygen which present in the compound like nitrate, sulfate, nitrite, all these compounds. So, they cannot use the molecular oxygen, but they use the oxygen present in the compound like nitrate, sulfate and nitrite like this. So, here that now here that the heat evolved in the aerobic fermentation process, we can calculate with the help of the equation, that is 4 into Q0 into B. Q0 is the approximately equal to 133 kilojoules per equivalent free electron transferred from substrate to carbon dioxide. So if you multiply it by B, that then we actually this will get give you the information kilojoule of calm atom of substrate consumed. Now here I want to show you something, that that Q actually Q is equal to 4 Q0 into B, and what is this is equal to kilojoule per gram atom substrate. Now question is that in the biological process we try to find out per unit cell mass formation how much is the product formation. So how you can find out? So here if you multiply it, suppose if you know that y x by s, y x by s is nothing but gram. Now so here what I can do, I can multiply this with the molecular weight of substrate, we can multiply it, and then y x, if we multiply molecular weight, they will be gram of substrate, kilojoule heat produced per gram of substrate, and y x by s is what? Y x by s is the gram of cell mass produced per gram of substrate. So that, so here I have written like this, that if you divide by molecular weight of substrate by yield coefficient, then you will get the information per gram cell mass formation how much heat is evolved. That you can find out. Suppose you want to produce 10 kg of Baker's yeast in the Baker's yeast fermentation process. So for the production of 10 kg of Baker's yeast, how much heat is evolved, you can easily calculate with the help of this equation. So this is all I want to tell about the stoichiometry of bioprocess. The next class I shall discuss about the different problems that we have with the stoichiometry of bioprocess, so that your conception will be little bit clear. Thank you.